Alrighty, let's get started. So this video is about magnetism. We're done with the electricity part, so we want to see what is magnetism. One thing we're pretty comfortable with is the idea of a bar magnet. You have this piece of metal. On one side is the North Pole, on the other side is the South Pole. And we know, and usually it's separated like that, we know that if we have another bar magnet, like here, if this side is north and this side is south, and I put it close to the other magnet, what's going to happen? Well, because very similar to electric charges, where you have positives and negatives, positive or like charges will repel each other, unlike charges will attract each other. Magnetism works very similarly. Instead of positive and negative, we call it north and south. So if you put the north pole of one magnet near the north pole of another, like poles will repel, unlike poles will attract. Okay? So very, very similar. And just like with electricity, we have something called the magnetic field. So we know with electric charges, a charged particle will produce an electric field surrounding it that propagates in all directions. And if you have multiple charges, then those fields all kind of add up together to create a total electric field. Magnetism works the same way. With a bar magnet, we get fields that kind of look like this. You go, just like with electricity, with charges, you go from positives to negatives. Well, with magnets, you go from north to south. Okay, so you've probably seen stuff like this. And these magnetic fields will interact, and just like with electric fields, the magnetic field will kind of dictate or tell you how a magnet will be affected, how it'll move, or what force it will feel due to the magnetic field it's in. Okay? So, if this is true, and it is, that the magnetism or the effect of magnets is very, very similar to electricity, is it also true that there's a north and a south charge, like there's a positive and a negative charge, right? If you have an atom, that atom is composed of a nucleus, which has protons and neutrons and electrons surrounding, and so you can split this atom up into pieces, and you can have the proton over here and the electron over here, and so the electron is a negative charge and a proton is a positive charge. Is the same true for a magnet? If we were to take a magnet that has a north and a south pole and we start splitting it, can I just take the south part or the north part of the magnet and take it separate from the south? And so we may try it. We may split this magnet down the middle, and then we take this piece over here, we take that piece over here, and what do we end up with? Well, we end up with something that looks like this. Here's your little broken piece. Here's this broken piece. And just like before, this side is still north, this side is south, but instead of it just being a north piece and a south piece, all of a sudden when we measure, this half has a north and a south now, and this half has a north and a south. Saying, well, that's kind of weird. I just took one magnet, split it in half, and now I have two magnets. Well, let's try it again. Let's split it again. This piece goes over here. This piece goes over here. Now what do I have? I've got this little piece, north right here. And I've got this piece, south over here. But unfortunately, again, we get the same kind of an effect, where the more we break each magnet up into halves, into pieces, each one of those pieces is a whole magnet. And we could keep trying this over and over, splitting the magnet over and over, until we get down to a single particle. We keep splitting it, Eventually we get down to molecules, we get down to atoms, and then we get down to the electron itself. And at that point you say, well, surely, once I get to an electron, that's one single thing. That's one electron, one particle. Is that going to be a north particle or a south particle? Well, when we look at it, it turns out, unfortunately, it's neither. It's actually both. because the electron has a spin, so we can imagine, now it's not really doing this, but we can imagine that this electron is spinning in some way. And depending on how it spins, counterclockwise or clockwise, we will give it a direction up or down. Let's say this one's up. And that would be the north, and the south part would be the down part down here. And so even a single particle, a single electron, which cannot be broken down any further, acts like its own little bitty tiny bar magnet with a north and a south pole. What this means is, although magnetism seems to behave very similar to electricity, it's actually different. Electricity, you have two sources of the field. You have positive charges and negative charges, and they can be split apart, and you can hold a single positive charge in your hand, and everything's fine. But with magnetism, the source of the field are not north and south charges or north and south sources, but the field is composed of a combination of north and south, even if it's a single particle, and this creates its own little magnetic field. So that's the first big difference, and in fact, it's such a hugely important difference that when we go further and we talk about Maxwell's equations, one of the four main Maxwell's equations tells you this specifically, that there is no such thing as what's called a magnetic monopole. Nothing like it. Electricity, there are. Positive charges are electric monopoles. Negative charges are electric monopoles. But with magnets, there's no such thing as a north pole, a north monopole. Just a little particle that's only north. Now, how does the magnetic effect actually happen? Because if you think about it, what the heck is the difference between a block of iron and a block of wood? Let's say you have some magnet, some natural magnet. It's got magnetic properties. You put another piece of that iron next to it, and they will attract or repel, depending. But if you have two pieces of wood, these pieces of wood are also made out of nuclei and electrons. These electrons are spinning just like the electrons in iron. There's nuclei in the iron, there's nuclei in the pieces of wood. So what's the difference? Why is iron acting like a magnet and wood not? The way to think about it goes like this. Say you have a piece of material. That piece of material, of course, is composed of a whole bunch of atoms. What I'm going to think about is only looking at the electrons for now, because that's all we really care about. What's happening with the electrons. We don't care about the nuclei. So all throughout this piece of material, you have a whole bunch of electrons. Every electron has a spin. And if you have some random piece of material, then each electron can spin in various ways, completely randomly. And it's just chaotic, right? Each electron has its own spin that spins in some direction, and there they are. So you could say like the total net spin of all these electrons is just zero. You got some up, some down, some left, some right. They kind of even out. But if instead you took this same material and you put it inside of a magnetic field, and let's say this magnetic field is pointing this way. Let's not worry about negative versus positive charges or anything like that. We put this piece of material in a magnetic field. By the way, the symbol for magnetic field is capital B, and it's a vector. So here's our magnetic field. We put this material in this magnetic field, and what happens? Well, these electrons, because they act like little bitty bar magnets, when they're in the presence of a magnetic field, they get affected by it and they want to line up with the field. And so, if you have a material where these electrons are free to move quite easily, then all of a sudden you're going to find all these electrons will line up with the magnetic field all in the same direction, pretty much. You may have one or two that go in the exact opposite direction, but for the most part, the vast majority line up with this external magnetic field. And then you can turn off that external magnetic field, and what you have is now a material whose electron spins line up in one single direction. And so if you think about this being a north and this being a south, this being a north, this being a south, north, south, north, south, you can see that you have north up here, but north down here. You have north to the right there, you got north to the left there. They're kind of canceling each other out. But on this other example, north is on the right, south is on the left, north is on the right, south is on the left, and it's all like that. So overall, you get this kind of southwardsness on the left and northwardsness on the right. And now you have what is a magnet. That's how magnets are made. Now, you say, okay, well, let's say I get a material that's not magnetic. Can I make it a magnet? This is how you would make it a magnet. For instance, I remember when I was younger and we had to deal with paper clips and things, a lot of times you'd have this little paper clip holder. It was like a, let's see if I can draw this thing, a little rectangular box with a hole, and all your paper clips are down here inside of this thing, and this lid, so this is the hole, this lid is magnetic. So this is already a magnet here, and then you have these metal paper clips sitting in there, and it's magnetic because some of the paper clips can just stay kind of at the top, so it's easy to pick them out. Well, after a long time, these metal paper clips being in the presence of this magnet, feeling its magnetic field, their own electrons will start to line up with that field. And so when you go to take a paper clip out, you'll get a whole bunch of paper clips stuck together. And not stuck together because they intertwine, that happens too, but rather stuck together because they are acting like their own little bitty magnets. And so you have a north side and a south side, and of course, just like with electrons or charges, unlike poles attract, so the south part of one wants to get with the north part of the other. But then if you take these electrons out of the container and leave it on your desk for a few days, you come back to them and all of a sudden they've lost their magnetic properties. They're not magnetized anymore. And that's because at first this external magnetic field forced all the electrons to spin in one direction, became a magnet. Then you took it outside of that field and you just left it alone. Well, energy is bombarding these paper clips. You've got the heat of the atmosphere, you've got air molecules hitting it, all sorts of stuff. And so this energy is kind of bumping into the atoms, bumping into the electrons, vibrating them. And if they have no real reason to want to continue to line up, then eventually these electrons start to reorient randomly again, and their magnetic properties start to cancel out, and they become demagnetized. Okay? But that's how that's what makes a magnet work. It tends to be, or it seems to be, that a magnetic field, a magnet is produced when you have some electrically charged thing, an electron, let's say. So something that has an electric charge, and that electric charge is spinning. So it's kind of this motion of the electric charge is creating this magnetic effect. It's the spin of the electrons that gives them the magnetic properties. And when they all line up in the same direction, these magnetic properties add up to become significant. If the electrons didn't spin, there was no such thing as electron spin, there would be no magnets. All right, fine. That's good. That's the theory behind magnets. What kind of calculation stuff can we do? Well, the first thing we want to do is, just like we did with electricity, is what if we have some kind of an electric charge and we move this electric charge into a magnetic field? So we've got some magnet out there creating a field for us, and now I want to move an electron through it, or move a proton through it, or whatever. Let's talk with a proton. And maybe we want to know, what happens to the proton? Does it feel this magnetic effect? It does indeed. In fact, when a charged particle moves through a magnetic field, it feels a force. So charged particles feel a magnetic force when they move through a magnetic field. Now it's important, the wording here, when they move through a magnetic field. If you have a magnetic field, here we go, and you place a proton right there and you just sit there, nothing happens. However, if you have your magnetic field, and now you get this proton, and you have the proton move with a velocity v, so this is a proton, and let's say it's moving up and the magnetic field is to the right, this proton is going to feel a force and it's going to bend. It's going to move. Instead of continuing to go straight up like it is here, it'll actually feel a force due to this magnetic field, and it's going to push it in another direction. In which direction will this force push it? It turns out that it's given by a cross product. So first let me write down the equation and we'll see how we get the direction and all of that. The force felt by a charged particle moving through a magnetic field is equal to the charge of the particle itself times V cross B, where V, that's the velocity of the charge, and B is the magnetic field. Now notice, because velocity and magnetic field are vectors, this is a cross product. It's one of those fancy versions of vector multiplication. And what does it tell us? Well, if you remember, the first time you see cross product in physics is probably torque. And with the cross product, if you have A cross B, the direction, the answer, will have a direction which is perpendicular to both A and B. So let's say A happens to be in the I hat direction, that's the X direction, and B happens to be in the J hat direction, the Y direction. When we do the cross product between A and B, we will get some answer C, whatever it happens to be, and the direction of this answer will be in the K hat direction, the Z direction. And then, of course, you have the permutations of this. So I cross J will give us K. J cross K will give us I. And K cross I will give us J. And then, if there's a reordering, so if you have I crossed with K, notice IJK. JKI, KIJ. It's always the same order. If I go off order, anticyclic, then you get a negative sign. So IK, notice I skipped J, so the answer is going to be J, but with a negative sign. Or if we have J with I, notice K was skipped, so K is going to be there, but with a negative sign. And then, of course, K with J, I skipped I, so I is going to be the answer, but he has a negative sign. Okay, so if you have the cyclic permutations, you get a positive answer. Anti-cyclic, you get a negative answer. But it's always I, J, then K, or J, K, then I. So if you have an X direction crossed with a Y direction, the answer is going to be in the Z direction. One way of doing this is you could use your right hand, the right hand rule, and you could the way I do it, so you have your right hand, let's see. Let's say you have your fingers pointing this way. Here's my beautiful picture. Like this. You put your fingers in the direction of the first guy, so let's say the I hat direction. So they're pointing out there to the right, and then you curl your fingers into the direction of the next, the other guy. So let's say A is in the I direction, B is in the J direction. Well, if I'm going to draw my axes, here's I hat, or here's, X direction, Y direction, so Z direction goes out of the page. So I would line my fingers up with the X direction first, and then I want to curl them into the direction of Y, so if I'm going from I to J. So in order to do that, I kind of have to flip my hand a little bit, so now my fingers kind of point, my hand is kind of sideways, so that I can curl them. Let me see, I'm not very good at drawing here. They're curled up like this. Okay, and my thumb is pointing out like that. That's a very bad drawing, but I hope you can understand it. So my fingers originally are pointing to the right, then I have to kind of flip my hand. So now my thumb is pointing out of the page towards my face, and I curl my fingers up to the upwards direction, because Y is upwards. And the direction of my thumb will always tell me the answer to this cross product, or the direction of the answer. So I was to the right, my fingers are to the right, I curl them up to the Y, my thumb automatically points out of the screen towards me, and so I know the answer has to be K. Okay, so that's a way of using your right hand to, if you're not doing the calculation, you just want to remember which direction it should be. Fingers go in the first vector's direction, then you manipulate your hands such that you can curl your fingers into the second guy's direction, and whichever way your thumb points when you do that, that's the answer's direction. This only works for the right hand, so that's why it's called the right hand rule. Okay, but if you just want to remember IJK, JKI, KIJ, cyclic permutations. What about how to actually get an answer, though? This is just telling me the direction of the answer. What if I want the number? What's the magnitude of the answer? Well, if you remember A cross B, the way you did it was you set up a little matrix, so this is one way to do it, where the first row are your directions. The second row are the components of your first vector, so AX, that's the X component of A, the Y component of A, and the Z component of A. And the last row are the same but for B, the X component, Y component, and Z component. And then we do the determinant of this matrix, which would give us something that looks like this. I hat times a Y BZ minus a Z BY. Then we subtract the next term, J hat times AX BZ minus AZ BX. And then we add the last piece, K hat times AX BY minus AY BX. This will be your answer. This is the official answer. It gives you both the magnitude and the direction. Whereas the right-hand rule thing is just a method of quickly determining the direction. Now we also saw that if these problems are kind of easy, then we could rewrite A cross B to be the magnitude of A times the magnitude of B times the sine of the angle between them. So if you have two vectors A and B, and you want to know the cross product between them, you look at the angle between them, that's theta, and you say, what's the magnitude of vector A? what's the magnitude of vector B, and then you multiply those two things by the sine of the angle between them, and that gives you the magnitude. This is the magnitude of the cross product. Okay? But this is how to actually get the full answer, magnitude and direction. All right, so what is this telling me? If we go back, this equation right here tells me something very specific. It says, what gives rise to a magnetic force? Here's a little vector symbol. Well, first of all, you need a magnetic field to exist. That's the B. You need to have a charge existing in this magnetic field. That's the thing that's going to feel the force. If you don't have a charge, it's not going to feel the magnet. And that charge has to be moving. It needs a velocity. But very specifically, because this is a cross product, that means you will only ever get an answer non-zero if V and B are not in the same direction. That's what the cross product tells you. That's why torque uses a cross product. Work uses a dot product. Work is all about how much of the force is in the direction of motion. Torque is how much of the force is perpendicular to the direction. And same thing here. We have the cross product between the velocity of the charge and a magnetic field that it's in. You only get an answer if those two things are not parallel. If the force, or if the velocity of the charge is in the same direction as the field, you're not going to get anything. The cross product is zero. So you won't feel a force. But once you allow this charge to move in a direction that's not parallel, it doesn't have to be perpendicular, that just makes it easier. But even if it's at an angle, you need this charge to be moving, first of all, and it has to move in a direction that's at an angle with respect to the magnetic field. Once you have that, then that charge will feel a force due to the field, and that force is given by this particular equation. So let's try an example. So let's say we have a proton moves along the positive x-axis with speed 10 meters per second. Okay? It is embedded in an external magnetic field of 0.2 Tesla. That's the unit, T for Tesla. That's the unit of magnetic field we're going to use in physics. So it's got a magnetic field of 0.2 Tesla pointing in the y direction, positive y direction. Part A, what is the force? What's the magnitude of the force felt by this proton? All right, well, force due to magnetic field is Q times V cross B. Now, when I go to do this, what I usually think is this. If V and B are perpendicular, then it's just V times B. You know, Q times V times B. If not, if V and B are at angles, then it's QVB sine theta. Okay? Obviously, if they're perpendicular, sine theta sine of 90 is just 1, so you get Q times V times B. If they're not perpendicular, then you just include the sine of theta at the end. Okay? So what do we have here? We have a proton moving in the positive x-axis. So here's my proton moving this way. We have a field which points in the positive y direction. That's our field. This is our velocity. And so those two things are perpendicular. Very nice. So force is equal to, well, this is the charge of a proton, so whatever that number happens to be, 1.6, I think, times 10 to the minus 19, okay, times the velocity, well, we're told it's 10 meters per second, times the magnetic field, that's 0.2, and because they're perpendicular, I don't need any sine theta, so I just plug these numbers in, and I get 1.6 EE minus 19 times 0.2 times 10, and I get the answer 3.2 times 10 to the minus 19 newtons. Okay? So if this were an electron instead, I get exactly the same answer, because a proton and electron have the same charge. One's negative, one's positive. But I'm always using positive numbers here because, for part A, I just want the magnitude. And so there it is. That's how much force it's going to feel. Now part B, I want the direction. In which direction will this force point? So we look back at the problem. The problem said I have the velocity in the positive x direction, so I need v cross b, right? Well, the direction of v, that's the positive x direction, that's I hat. And then I've got the magnetic field that points in the positive y direction, so that's the positive j hat. And when I take the cross product of I times j, I get positive k. So there we go, positive k hat, or the positive z direction. Okay, either one. You can either say k hat direction or z direction, positive z. Now here's something to be careful about. If instead of this being a proton, I said this was an electron, I said for part A, you'd get the same answer. Because there's no difference between the charge of a proton or an electron, except that the electron is negatively charged instead of positive. But because the magnitude doesn't want positives or negatives, you just give the answer. But for the direction, it does matter very strongly. So this V cross B business, this is assuming this is a positive charge. If instead of saying this were a proton, I said this was an electron, then whatever answer I would have gotten for the direction, it's the opposite direction for the electron. So if electron, the answer would be the minus z direction instead of the positive z. Okay, so very easy. Just remember the right-hand rule, and then at the end, remember, that works for the positive charges. If your problem had a negative charge instead, just flip the direction at the end. Everything else remains the same. So that's the magnetic force acting on a moving charged particle. Okay, again, if it wasn't moving, what's the magnetic force? Well, V is 0, so obviously the magnetic force would be 0. If the magnetic field is this way, and my charge is moving that way, or this way, then you know automatically the force felt by this charge is 0, because the velocity vector and the magnetic field vector are the same direction. But in order for a cross product to give you an answer, they can't be parallel. They have to be at angles at some point. In this case, it happened to be perpendicular, but you can imagine a problem where they're not perpendicular, where they're parallel or something. All right, so that's magnetic forces. What else do we have? Well, let's say we have, a long wire. So here's a wire. And our little electrons are in this wire, or protons, of course, but we'll think of them as electrons for now. And these electrons are moving through the wire, right? That's called a current. Electrons moving through the wire, we call that thing a current. It's just moving electrons. Of course, the direction, as we see when you take circuits class, unfortunately, the standard is that we call the direction of the current to be the opposite direction of the motion of the electrons. So the electrons move to the right, we say the current moves to the left. It's just a problem with the original definition, thinking they were protons instead of electrons, but whatever. So now the question is, okay, well, let's say I have this wire with a bunch of electrons in it moving, so I have a current traveling through this wire, and I put that wire in an external magnetic field. Notice, if we don't think about it as a wire, but we just think of one of these single bitty electrons moving to the right, well, that's a charged particle moving with a velocity which is at an angle relative to this magnetic field, so that electron should feel a force. And there's a whole bunch of these electrons doing that, and they're all placed inside of this wire, so this wire should feel a force. So the question is, if you have a wire, sometimes we'll call it a current carrying wire, so that's a wire that has a current moving through it, and you place this wire with a current inside of a magnetic field, what kind of force will the wire feel? So that's the force on a wire rather than a single charged particle. How do we do this? Well, the way you do it, you start with your original equation. You say, look, I've got Q times V cross B, right? Now, what I'm going to do is I'm going to say, do you remember what V is? In physics, V is delta X over delta T, right? Or dx dt, if you want to do the calculus way. And so now I'm going to rewrite V like that, delta X over delta T cross B, right? And now I'm going to take this delta T and I'm going to put it outside onto this Q, so I have Q over delta T times delta X cross with B. And now Q over delta T from circuits, that's just current, right? It's the number of charges moving through your wire every second. How many charges flow past you per second? Q over T. Delta X, I'm going to call this how much of the wire we're talking about. So I'll call this length of wire. And I'll give it the symbol L, script L. And of course B is still there, so we have our equation. The magnetic force felt by a current carrying wire is given by I L cross B, or I L B sine theta. And there we go. So a problem like this may say something like, you have a 2-meter long wire placed parallel to an external magnetic field of 1 Tesla. If the wire has a current of 0.5 amps, what is the magnitude of the magnetic force felt by the wire? Okay. Well, the answer to that question, if you think about it, is 0. Because I said the current carrying wire is placed parallel to the magnetic field. And if it's parallel, so here's the field, push to the right, and we have our wire, which has our little electrons with the current moving this way. Well, that means the velocity of these electrons are in the same direction as the field, and we already saw from the first equation, the force felt by a charged particle that's parallel is just 0. Now, if we just have 1,000 of these guys, it's still 0, because it's just 1,000 zeros. The only way to get an actual answer, because it's a cross product, is for there to be an angle between the magnetic field and the wire. So you might have something like, here's our field, And our wire maybe is like this, and it has a current I of 0.5 amps, and a magnetic field B is 2 Tesla, and maybe the angle here, theta might be 30 degrees. And the question is, what's the force felt by this wire? Well, we just use this equation right here. We know the current I, and we need to know the length of the wire. Let's say the length of the wire is 2 meters. You know the length of the wire, so that's kind of like how many electrons are there. You know the magnetic field strength, you know the current in it, and you know the angle. So we just do ILB sine theta. That gives us the magnitude of the force that this wire is going to feel. Now the last thing I want to go through is, well, let's take this wire, instead of it being a straight wire, what if we made it a loop? So a loop of wire. So here's our loop. Okay, and now we're going to let the current flow through this loop, so it's going to have some current I, and we're going to take this loop and put it inside of this external magnetic field B. And I want to know, will this loop of wire feel a force? So this is interesting, because if you look at where the current starts kind of parallel to the field, right? The field is to the right, the current's to the left, they're parallel to each other, so it's not going to feel a force. But as soon as it moves just a little bit, now the current is at angles, and it's perpendicular here, it's at angles, then it gets parallel again. So as this current flows around, it will feel kind of a varying force in a way, sometimes zero, sometimes maximum. So yes, I expect, even though this loop of wire is currently flat, parallel to the magnetic field, because when the electrons go around the loop, they are going to be at angles at some points, it's going to feel a force. Now the kind of force this loop is going to feel is going to be a torque. So if you have this loop of wire and you put it in the magnetic field and you turn the current on, the loop is going to spin to try to align so that the magnetic field goes through the center, let's say. But at the very least, it's going to spin. So it's going to apply a torque to the loop to try to spin it. So we want to know, what kind of torque will this loop feel? How do we get this? Well, we say, okay, we start with the original equation. F is I L B sine theta. Right? That's the force felt by a wire with a current that's placed in an external magnetic field. Now, instead of force, we want torque, and remember, torque is R cross F, so it's like force times distance. So I'm going to multiply this guy by a distance, and so I need to multiply this guy by the same distance, right? So now, F times X, we could call that the torque, tau. And what do we get here? We have I. And now what I'm going to do is I'm going to take this X and multiply it by L. And if you look at the units of this, you have a length times a length. That's a length squared. That's like an area. Okay? So that's the area times B, the magnetic field, times the sine of theta. And so there we go. We have the torque, which would be felt by a loop of wire. That loop of wire has an opening, so it has an area. You know, area is your pi r squared business. So maybe I tell you the loop has a radius of 0.1, 10 centimeters or whatever. So the loop of wire has some area, some opening area. It's placed in a magnetic field, the current's on, and this loop will be at some angle relative to the magnetic field, at least the opening of the loop. And we want to know with what torque will this loop be spun because of the magnetic field. We would use this equation right here. Okay. So we have three big equations, right? We have F, the force felt by a single moving charged particle. So F on charged particle. is equal to Q times V cross B. We have the force felt by a wire placed in a magnetic field. And I'm going to get rid of the cross product just for now, just to make it more usable. ILB sine theta. And we have the torque felt by a loop, which is IAB sine theta. Now, one modification is, let's say instead of a single loop, I have a coil. So maybe there's this loop of wire and I loop it around 10 times. So there's 10 loops of wire here. How does that affect it? Well, we just multiply this answer for one loop by the number of loops there are. So if you have a coil of wire that's composed of 10 loops, then N would be 10. You have 10 loops of wire instead of just one loop of wire. Okay? Now, you can memorize these, but I never memorize them. This is the only one I know off the top of my head. V cross B. The other two, I just get exactly how I derived them for you just now. If I want the force on a wire, well, I just make that little trick where I take V and I change V to dx dt. The dt goes with the Q to make it an I, and the dx becomes the length, and now I have my new answer, or my new equation. If I then make that wire a loop, now I want a torque instead of a force, so I got to multiply by an extra distance. That extra distance gets put onto the length to make it an area, and then I can have as many loops as I want. So it's N, the number of loops, times IAB sine theta. Okay? And that's what we need to know. These are the force equations we need for magnetism. Again, the big things to take away: cross product. That means these things, V and B, or I and B, or things like that, they have to be in the same, or they can't be in the same direction. If they're parallel, you get nothing. If they're at an angle, or even better, if they're perpendicular, that's when you get some force. The direction from a cross product, you just think of the cyclic permutation, I, J, K. So I crossed with J gives me K. If it's anti-cyclic, if it's the wrong order, so I crossed with K, that gives me minus J. So it always goes from I, J, K. You have all three. But is it positive or negative? Well, if it's cyclic, I, J, K, J, K, I, or K, I, J, then it's positives. If it's anti-cyclic, if it's the wrong order, then you get negatives. And you can do other things like, you could have minus I crossed with J. How do I do that? I just pretend the negative sign isn't there, and I look at it's I cross J. That gives me positive K. But then because there's this negative, I have to put a negative on the answer. Or I can have negative I crossed with negative K. What is this? Well, I get rid of the negatives for now, and I say, what's I crossed with K? That's anti-cyclic, so it's going to give me a negative J. But then this negative makes him positive, and then that negative makes him another negative. So overall, this is minus J. Okay, so very easy to work with the directions once you know the cyclic permutation rule. And then the other thing to worry about is, remember, if instead of this being a proton, it's an electron, then the directionality is the opposite. If we're talking about an electron in this magnetic field moving, then I crossed with J would give me a negative K, because it's an electron. It's still K, but the electron goes in the other direction, I should say. All right, so I hope this is helpful. These are the big equations you need to know to be able to do these calculations. There's really not too much to it. I won't go too many times into the true cross product version. Most of the time we're going to use this sine theta business. You know, you'll have, here's a magnetic field, here's your wire, so here's the B, there's the I, and this angle maybe is theta. And you say, okay, well, it's ILB sine theta, so I know what I is, I know what B is, and I know theta is 30 degrees or 40 degrees, whatever it is, and I get my answer. I don't have to do the true cross product there. All right, anyway, that's all I have for you today. I will see you next time.